And if you come in late, make sure that you talk to me after class so I can make sure that I put you as attending on the roll. Section 2.4 is going to deal with measures of variation. We're going to determine how to find the range of a data set. We're going to determine how to find the variance and standard deviation of a population and a sample. And we're going to learn how to use the empirical rule and Chebyshev's theorem to interpret standard deviation. And we're also going to talk about how to approximate the sample standard deviation for group data. Now, when we talk about measures of variation, what we're talking about is looking at the distribution, whether it be a population or a sample, and looking at the mean, and looking to see how all the data values in my distribution deviate or vary from that mean. Okay? Even though I said on Tuesday that the better measurement is the median, for these calculations we're going to use the mean. Because we want to use a measure that is affected by outliers in this case. Because the analysis that we're going to do now is going to help us understand the behavior of the distribution. So the first thing that we talk about when we deal with measures of variation is the range. And we have to have the range in order to do this. And the range is simply said, you take the data set and you find the difference between the minimum and the maximum value. The easiest way to do this is to put it into numerical order from least to greatest. You've got the smallest, you've got the greatest, or you can do it from the greatest to least, okay? And then you can find the range. It's the maximum data value or entry minus the minimum data value or entry. And it's not that difficult to find a range on a small distribution. If it's a large distribution and you have to find the smallest value and you have to find the largest value without the benefit of a computer, it becomes a little more difficult. It's very easy to miss a number, okay? But let's look at try it yourself number 1. And we're going to be working with this data set for the try it yourself number 1. Now, for the try it yourself number 1 here, move some stuff around to make it. It says find a range of the starting salaries for Corporation B. You want to identify the minimum and maximum values, and then you want to find the range. Now, if we look at this, a couple things that we need to pay attention to. This is in thousands of dollars, so that the starting salaries, for example, that first one is actually $40,000, then $23,000, then $41,000. This is a technique that we use a lot in statistics and in a lot of math, simply because it makes my calculations easier. I don't have all these trailing zeros to deal with. So if I maintain a multiple here, like in this case thousands of dollars, I don't have to write out 40,000, 23,000, and so forth. And what does that do for me? Well, number one, my data table is a whole lot more concise than it would be if I had to write each one of these as a multiple of 10. Okay? So let's go ahead and identify the minimum value, which in this case is 23. That's our minimum. And then we're going to identify the maximum value, which is 58. And then to find a range for this, we're just simply doing the maximum minus the minimum which in this case is simply 58 minus 23, and I get 35. So the range is actually $35,000. That's how you would write it down. You wouldn't write it as 35. You would state that the range is $35,000. Okay? That's how you would indicate it. Now, obviously, in my stat lab, you're just going to have to type the number in. But if you were actually writing it out for a report, or if we were doing this as a paper and pencil test, that's how you would indicate it. All right, range is actually pretty easy. Another thing about range is you can find it fairly easily using either StatCrunch or Excel. Okay. For example, in what happened to StatCrunch? I thought it was there. Oh well. If I'm in my stat lab and I want to find the range of a data set, I just simply go into StatCrunch, and in this case I just copied the data table into StatCrunch. Wait for Java to load because it is slow, especially on this computer. And there we go. So let's look at book number 1. If I want to find a range of book number 1, I click Stat, Summary Stats, Columns. And I want to do book 1. Click Next. Now notice that range is right here. I just went ahead and took the highlight away from it. But I can also find the minimum and maximum value too. If I left click that, come back to calculate. Oops, that's not what I want. There we go. This is from the homework set. Notice that it gives me the range right here at the end. It also gives me the minimum and maximum values if I want them. Okay? Any questions? You can do the same thing in Excel. I just use StatCrunch because it's integrated into StatLab, which, you know, how many of you guys are actually trying to use StatCrunch when you're doing your homework? Good. Everybody needs to be doing that, because trust me, when it comes time to take this test, you don't want to have to be doing a standard deviation by hand on the test. Even though I give you a 3-hour time limit, it's going to take you longer than that if you're doing everything by hand. Get used to StatCrunch or get used to Excel, whichever one. They've got them loaded on the computers that you can take these tests on over here. Okay? Still working on the ones in Huntsville, so for right now, if you're going to take these tests, unless you want to do everything by hand, which, trust me, you don't. Okay. All right. Any questions on range? Let's talk about deviation. Okay. In the textbook, we talk about deviation. The deviation of an entry, X, in a population data set is the difference between the entry and the mean, mu, of the data set. So your deviation of X is equal to X minus mu. What does that really mean? Well, and I'll come right back to that, so don't get all stressed out. There we go. All right. I have, let's say, the data values here. Okay. And I'm going to look at these data values. This is my population. Okay, I'm going to define this as my population right here. This is a data set for my population. Okay. I need to find the mean of this thing, okay, to actually be able to understand deviation. But the first thing that I want to do is reorder this, okay? I want to put this in numerical sequence. So I'm in Excel on this one. And you can do it in StatCrunch too. I just happen to have the data set here. So I'm just going to go ahead and sort and filter this thing, and I'm going to do an A to Z, which means least to greatest. Okay, and that's what I've done. So now that I've rearranged my data set from least to greatest, I'm going to go ahead and look at that. So this thing has been sorted. It's now sorted. And then what I need is the mean in order to find any sort of deviation. So let's find the mean. How do I find the mean? Well, I go into Excel, I highlight that, and I'm going to come over here to Formulas, More Functions, Statistical, and I'm going to click Average, and I'm going to click OK, and there's my mean, 32.26. Now I can do it in StatCrunch if I want to. Let's copy that. Let's go into StatCrunch. And I'm going to go ahead and, well, I thought I was going to paste it. There we go. I loaded it. Okay. All right. Now, I can do the same thing here. If I go to if I go to Data, come down here to Sort Column. I messed up. Edit. Cut. Well, let's go ahead and load data again from paste. Yeah, there's something that you need to remember. If you click Paste Data from Clipboard, you need to... We're back here now, and we know that the mean is 32.26. And we're going to write that down here, and I'm going to write it in a different color. So it's 32.26. And that's my mean, and we're going to use the Greek letter mu because it's a population. What symbol would we use if it was a sample? X bar. Good. Okay, now let's go ahead and figure out where 32.26 sits inside the distribution. Well, the mean is going to fall right between these two values. Okay? Now, what I want to do is let's pick a value. I don't care, any value. For example, this one, 36.5. Let's just choose 36.5. And I want to know what is the deviation of this value from the mean. And the deviation is simply equal to x minus mu, and in this case, x is the 36.5, and we're going to subtract from that mu, which is 32.26. And that's going to give me, I don't know, that's going to be 4.24, right? Somebody double check my math. Okay. So that's the deviation. Now, this is a positive value. What if I were to pick one of the values over here? Would that be a positive or a negative value? It's negative. So the deviation can be both positive or negative depending upon where the data value is located in relationship to the mean. And that's an important concept because at some point when we start doing analysis, we have to account for negative and positive values. Because if we have negative values, they're going to start to eat away at the positive values. And we don't want to have that. So at some point, we're going to figure out how to square these things and take out the possibility of negative values skewing our data. Even though I still want to be interested in what's happening to the left of the mean and what's happening to the right of the mean. And when I say left and right, what I'm talking about, the left are numbers that are less than, notice the alliteration, left, less than the mean, and the numbers that are right, that are to the right of the mean are the ones that are greater than. Okay, there's no alliteration on that one, but you know. Okay. So the mean, the deviation from the mean can be positive or negative. Okay. And like I said, we were talking about looking at numbers that were to the left of the mean and to the right of the mean. Well, once again, let's just identify. These right here are all my values that are greater than the mean. Or I should say to the right of the mean. Now, when I say to the right of the mean, that's going to start to make more sense when we start putting these things in a distribution graph and come up with either a normal distribution or a uniform distribution or a left or right skewed distribution, but we're going to graph it. And we're going to have the mean in the very middle. And values are going to occur to the right on the graph, and values are going to occur on the left of the graph. And so these right here are less than the mean. Or to the left of the mean. And I know I just said that a few minutes ago, but I want to have you guys have some sort of visual representation. And if I were to just take this distribution and turn it this way, the mean's still in the middle, but then I've got these numbers here to the left and these numbers here to the right. And that's really what we're going to be doing. Now, this also works if I'm dealing with a sample. But like we said, instead of using mu, we'd use x bar. And a lot of these formulas that we're going to be introducing here in just a few minutes are based upon population, and then we have another set of formulas based upon sample. And they're really close. They're very similar. And there's only like one minor difference between the two. But if you don't pay attention to that one minor difference, it's going to destroy your analysis. Okay? I better not use that anymore. Anyways, I'm sorry. That's how twisted I am. So let's talk about deviation, or definitions of variance, I should say. All right, here's our first real formula. And I know we've had a couple, we had the mean, and, we've looked at the range. But this is the first formula that actually is going to have some meat to it. Where if you're not careful, you can really mess up. Okay? This is the population variance of a population data set of big N entries, N being the total number of entries. The population variance is given by the lowercase Greek letter sigma, and it is squared. So we call it sigma squared. The variance is sigma squared, and that's equal to, and this is a capital letter, the capital Greek letter sigma, the summation of x minus mu quantity squared. Now what that means is I'm going to take every single data set and I'm going to subtract the mean from it. And then I'm going to square it. And then I'm going to add all of those together to get this value right here. And then I'm going to divide by the total number of values in the data set. Okay? So that's my formula for population variance. Now, in addition to variance, we have something called standard deviation. And standard deviation is taking that deviation that we were just talking about, the x minus mu, and standardizing it. In other words, making it so that every single value in my data set can be compared back to the mean, and those values are going to be positive. Okay? The population standard deviation of a population data set, once again of n entries, is the square root of the variance. So it's just lowercase sigma. Sigma is equal to the square root of sigma squared, which is this, so it's the square root of this. So here's my formula for standard deviation. It's the square root of the summation of x minus mu quantity squared divided by n. Now, I know that makes perfect sense to you guys, and you guys are ready to roll, right? Yeah, no, you're not. You guys are going, what? Okay. And this is what math is about. Mathematicians sit there, they come up with all this stuff, and then they throw out all these arcane formulas, and they expect the rest of us to figure out exactly what they're talking about. And sometimes you can, sometimes you can't. So what I'm going to do is give you some guidelines here for doing the standard deviation. And we're going to actually work out a standard deviation by hand, and then we're going to calculate it using StatCrunch and Excel. And you'll see the difference. And trust me, the difference is night and day. Okay. Now, as far as the guidelines go, they are in your textbook, and they are on page 82. But the textbook does such a nice job and I want to go ahead and bring this in. Did everybody get the standard deviation formula? Okay. All right. Now, how do we find a population variance and a standard deviation? The first thing that I want you to do, and it doesn't say this here, and I'm going to put this in as a preamble, is order the data set. And we want to go least to greatest, okay? Now, that should become standard in your head. Anytime I got a data set, I'm going to order it least to greatest, okay? I want you to do that. I don't care what the textbook says, all right? Once I do that, I need to find the mean. And I know how to find the mean. I add all the values together and divide by the number of values. Then I'm going to find the deviation of each entry, which we talked about, x minus mu. And then I'm going to square each one of those deviations. And then I'm going to add to get the sum of squares. Now, when you see this symbol SSX, SSX means sum of squares. In other words, it's this right here. Sum of squares. And I know they write it right there. But SS means sum of squares. Okay? Once you do that, you're going to divide by n to get your population variance. Once you've got the variance, just take the square root and you've got the standard deviation. And the standard deviation is really cool because it's going to allow us to create, or I should say calculate, something called a z-score. And eventually we're also going to calculate t-scores. But right now, let's concentrate on z-scores. Z-scores are going to allow us to define how far away data values are from the mean in either a positive or negative spectrum that range from 0 to roughly 4 or 5, either in the positive direction or the negative direction. They can go beyond that, but generally speaking, you're not going to see a z-score that's either less than -5 or greater than 5. Don't worry about that if you don't truly understand that now. You will by the time I'm done with you, or at least I hope you will. Okay? So, what I want to do is go ahead and do one of these things. I want to find the variance and standard deviation of a data set. And we're going to use the data set of the salaries, the starting salaries for the corporations that I had first pulled. Okay? Now remember, this stuff is in your textbook, and I do post these notes online, and everything online is up to date through 2.3. Okay? So you can go into Blackboard under content. How many of you guys have actually done that? Good. It's actually starting to pay off. I've only been doing that for 8 years now. And finally, I've got a class that the majority of the students are looking at the notes. I don't know why I keep pounding my head against the wall. As Einstein once said, the definition of insanity is doing the same thing over and over and over again, but expecting different results. I keep putting the notes in there, and I expect that everybody's going to view them. I don't know why. Call me crazy. No, don't. I'm really not. But, of course, said the crazy person to the psychiatrist, right? If you guys haven't noticed, I am just a little left of center, okay? I tend to look at things a whole lot differently than the rest of the world. Okay, try it yourself. 3. You want to find the population variance and the standard deviation of the starting salaries for Corporation B, given example 1. They tell you what to do, okay? Find the mean in each deviation. Square each deviation and add to get the sum of the squares. Divide n to get the population variance, and find the square root of the variance to get the standard deviation. Then it says interpret the results by giving the population standard deviation in dollars. Okay. So, let's go ahead and bring in that salary matrix that they had given us. Assuming I can find it again. Oops, too far. There it is. Now, starting salaries for Corporation B in thousands of dollars. Okay. First thing that you need to do is go ahead and create a table. Okay? And the first column in the table is going to be X. And that's going to be your salary values. But I want to put them in order of least to greatest, which means I start with 23. And then I'm going to go to 29. And then I'm going to 32. And then 40, and then 41, 49, 50, 52, and 58. So I want to make sure that I've got all of them. Let's see, I got 32, there's 40, 41. Oh, there's 2 41s, aren't there? So I missed one. That's no big deal. I just misread my notes because there's 2 41s in my notes. Okay? And so I've got all the data values. Okay? Now, the next thing I want to do is calculate the mean. Okay? The mean for this thing, mu, whoops, is equal to the summation of x divided by n, which in this case is 415 divided by 10, which is 41.5. Because if I look at my table, right here, I can do sigma x, and that's equal to 410. Okay? Now let's go ahead and find the deviation. The deviation is the x minus mu. Okay? So for this first one, I don't know. Is it 415? I wrote 415 up there. Yeah, it's 415. Why did I write 410 there? I have no idea. Let's fix that, shall we? There we go. And that's, so we have 41.5 is my mean. So, this first column is x minus mu. So that's 23 minus 41.5, which is going to be equal to negative 18.5. Notice that it is a negative number. Then the next one is going to be 29 minus 41.5, which is equal to negative 12.5. Then we'll do 32 minus 41.5, which is equal to negative 9.5. And I'm just going to write down the rest of the differences without actually writing out. And you don't have to necessarily write the 23 minus 41.5 in your table as you're doing it. You can just go ahead and calculate it. Now, one of the things is you can actually use Excel to do this for you. Click in the first cell next to 23 and then type in equals, and you're going to say whatever that cell is minus 41.5. And then just hit enter and it will do it for you. You can also put 41.5 in some other cell somewhere and use that as a reference call back. Okay? But for right now, we're going to do this. Okay? And this one's going to be negative 1.5. Negative 0.5, negative 0.5, 7.5, 8.5, 10.5, and then finally 16.5. Okay? Yes? You just type it in, or copy it in if you're in if you're in my stat lab. Click that blue icon, and it will copy it to your clipboard, and then you can copy it into Excel. If you give me a minute, I'll show you after we do this. Okay. All right. Now what I want to do is take that x minus mu and square each one of them, which means that I'm going to take negative 18.5, and I'm going to square it, and I'm going to get 342.25. I'm going to take negative 12.5. I'm going to square that and get 156.25. And I'm going to do that for each subsequent value in x minus mu. 90.25, 2.25, 0.25, 0.25, 56.25, 72.25, 110.25, 272.25. Okay? So, this is my first step right here. This is my second step over here. This is my third step. And this is now my fourth step. My fifth step is going to be to add this column up. That's my sum of squares. My SS sub x, or just simply sigma x minus mu squared. However you want to write it. And so, as I said, this is my fifth step right here. And the sigma of x minus mu quantity squared is equal to 1,102.5. Okay? Does everybody understand what I've done so far? Now I want to find the population variance. This is going to be my 6th step. And I find the population variance, which is sigma squared, and that is simply going to be equal to the sum of squares divided by n, which I already know what n is because I've got it up here as n is equal to 10, correct? So I'm looking at 1,102.5 divided by 10, which gives me 110.25. That's the population variance. What I want to do is find the standard deviation now. So, as I said, this is the population variance. Okay. My last step is to find the standard deviation, which is simply sigma, which is the square root of sigma squared, which is the square root of the sum of the squares divided by big N. Now, do I have to rewrite everything? No. All I got to do is say, look, this is the square root of 110.25. But let me say this. Let me warn you here. What I've done here is a simple distribution. These numbers do not lend themselves to what we call round-off error. Because if you've got a distribution where you're getting long decimals after the decimal point and you tend to round to 2 or 3 decimal places, you have changed the value of your data values. Okay? And what we would try to do is do as little calculating as possible until we get to the end. In other words, I'd do the squares, I'd add them all up, and then I'd divide by this number and take the square root at the same time. I'd do it all at the same time. That way I try to mitigate round-off error. In this particular case, it's not such a big deal. And so my population standard deviation is 10.5. That's, as I said, the population standard deviation. Now, what is standard deviation? Standard deviation is taking the variance from the mean and standardizing it into a positive value so that I can establish intervals out from the mean. And what I'm hoping to see is a pattern. I want to see as many values as possible fall within one standard deviation of the mean, either to the left or to the right. And then, of course, we can look to see if there's any values that are falling within 2 standard deviations, and then 3 standard deviations, and so on and so forth. Standard deviation is one of the yardsticks, the measuring tools that we use to determine if our data set, our distribution, has normal spread, or are there unusual values in here that we need to further investigate. Okay? One of the things that we did as a class last time, or one of the times that I taught this, was to look at the demographics in Huntsville of the socioeconomic climate. As far as what we did was we broke it down by race and by gender, and then we looked at average annual salaries. We broke it down into mainly the 3 major demographic groups that are represented in Huntsville. There are others, but we broke it down by white, black, and Hispanic. Okay? The actual definitions in the study was Caucasian, African American, and Hispanic. Okay? And then what we did is we looked at the national distribution for African American, Hispanic, and Caucasian, and looked at salaries. And then what we wanted to try to find out is there a main difference between the average annual salaries in Huntsville for those three demographic groups with comparing that to the demographic groups at the national level? And there was actually quite a big variance. Then we also looked at it across the demographic groups. We looked at Caucasian, African American, and Hispanic, and found that nationally, Caucasians earn more, then it's African American, then it's Hispanic as far as a group on an average annual salary. Whether or not that's fair was not the point of the study. What the point of the study was is, what is the difference? But then we found a huge flip. Caucasian, Hispanic, and then African American in Huntsville as far as the spread and the distribution for salaries. It was Caucasian with the highest salaries, then Hispanic, then African American. Once again, the purpose of the study was not to determine right or wrong, it was just to determine what existed. And then, of course, what we wanted to do, and we're going to do some studies in here that are not actually part of the syllabus, but we'll throw them out at you guys. One of them is going to be an M&M study that we're going to do, where you guys are all going to buy 2 bags of M&Ms, the little ones. And Mars M&Ms has a website that talks about the distribution of the colors. And we're going to take them to task and find out if that's actually true or not. But anyways, I digress. Then what we did with that study is determined why we might think that there were those discrepancies. Now, we're not talking mainly about the discrepancies between the fact that the Caucasians were making more than the African Americans making more than the Hispanics, because that is actually a well-documented problem in this country. In order to achieve true homogeneity, in other words, everybody's making the same thing, whites, blacks, Hispanics, Asians, Middle Easterners, they all need to be making the same thing. Likewise with males and females, because we further broke the study down by males and females, once again finding that males make more than females, even if you looked at the 3 demographic groups. But why is that so? Well, number one, we're a prejudiced society, unfortunately. We are. I mean, anybody want to debate me on that one? I mean, because we are. Right or wrong, we are. And that's not just in one demographic group. It's across all the demographic groups. Number two, we're a gender-based society, unfortunately, because let's be realistic, the whole power structure of this country was initially based on white gentried males. In other words, they were the landowners. They're the ones that created the government. They're the ones that ran the government for 60, 70 years before the Civil War. And then after that, we actually started to achieve some sort of parity. But then the idiots in the KKK came along, destroyed Reconstruction, and set back all the achievements that the South had made by another 50 years. And it wasn't another 100 years until things started to hopefully turn around again. And if it hadn't been for Dr. King and his marches on Washington, we still would be in the stupidity that we existed in before. But the statistics only tell me one thing. At the national level, whites make more than blacks, make more than Hispanics. At the local level in Huntsville, whites make more than Hispanics, make more than blacks. Why? I don't know. The purpose of the study wasn't to find out why. But we put forth some suppositions. Number one, what was the unemployment level nationally versus locally when the data was collected? Was the African American population in Huntsville hit unusually hard by an unemployment problem versus at the national level, which would explain why they were making less at the time that the data was collected? Also, was it a complete study? For example, did they, whoever did the study, because I found the data on the... Okay, we still got time, right? Are you just bugging out? Okay, all right. Sometimes I go over and I don't even realize. Was the data complete? For example, did they poll 1,000 white people 5 Hispanics who happen to make more than every other Hispanic in the entire, and then, 8 African Americans. And you can see where the disparity would come from. That wasn't indicated in the polling data. So these are things that we want to try to mitigate, in other words, smooth out by going with standard deviation and making sure that our samples are representative. Because I can skew data all over the place. Okay? I can look at salaries and I can take a large chunk or I can take a small chunk. But I don't have to tell anybody because I'm not going to publish that part of the study. I'm just going to publish my results. That doesn't mean my results are good. Doesn't mean that they mean anything. Okay? So, if I teach you nothing else in this course, is to make sure that when you're collecting data, you're doing it according to the methods that were introduced in Chapter 1, and we're making sure that we are looking at a realistic cross-section of the population. Because you're not going to sample the entire population. But your samples have to be representative. Okay? Let's just look at this class, for example. And let me just say this. When I break things down by race or gender, in no way, shape, or form am I saying that one race is better than another or one gender is better than the other. That just happens to be a very convenient demographic breakdown. Governments use it all the time. Okay? Sometimes for good, sometimes for bad. Okay? Corporations do the same thing. Why? Because the government's telling you, hey, I need to know how many white people you have working here, how many African Americans, how many Hispanics, how many Asians, how many Middle Easterners. Why? Because we want to try to do what? I can't hear you. Make it equal. We want to try to level the playing field. Now let's be realistic. Human beings being what they are, the playing field is never going to be level. And I'm not saying that from a one race is superior to the other. I'm saying as a bunch of collective individuals, some people are going to achieve more than others. That's just how we're built and designed. Is that fair? Well, I don't know. Does fairness need to play into it? What is it that you want to achieve? And that's kind of what we're trying to do with this, is let's look at the statistics and see if we can do that. Okay, now, let's finish what we're doing here. Because now that we've done this, we want to go ahead and talk about sample variance and sample standard deviation. They are different. The formulas are different. Not much, but they are different. Okay. You'll notice that in this one, instead of using the lowercase Greek letter sigma, we're using S to represent sample variance, or I should say sample standard deviation, and S squared to represent sample variance. What's the main difference between the two formulas? Well, aside from the fact that this is an S and not a sigma, it's this right here. Instead of using n, the entire group, we use little n minus 1, which means that if there are 15 values in my data set, I'm only going to divide by 14. And that's the main difference. Okay? The whole process is exactly the same as what we did for the population variance and the population standard deviation, except instead of dividing by n, we divide by n minus 1. Okay? Now, the textbook also gives you the guidelines for calculating sample variance and sample standard deviation. And honestly, it's exactly the same. We've just changed some things, okay? And let me just bring that in, and then I'll make sure you guys can all copy everything, okay? So just I'll give you the few minutes that you need. Okay. All right. Once again, I want to make sure that we go ahead and order from least to greatest. Or sort them from least to greatest, however you want to put it. And we do the exact same thing. We find the mean. Now, instead of using mu, we use x bar. Instead of big N, we use little n. Then we're going to find the deviation of each entry, x minus x bar. Excuse me. You're going to square each deviation. Then you're going to find the sum of the squares. Then you're going to divide the sum of the squares by n minus 1 to get the sample variance. Then you're going to take the square root of the sample variance to get the deviation. And I mean the standard deviation. Now, this is a time-consuming process. Incredibly time-consuming. The thing about it, though, is because of advances in technology and software, we can do it pretty quickly. The hardest part is actually entering the data. Okay? You can use Excel to find this, and you can use StatCrunch. StatCrunch is easy, because I only got to click one or two things. Okay? We're going to go back to the data set that I was using before, that I went ahead and found the mean for, and then we were talking about the deviation and everything. If I go back into StatCrunch, and this third column right here, sorry, why are you not? That third column right there, that's the one that I'm going to key on. Okay? This one right here, if I want to find the standard deviation and the variance, once I've got my column in there and sorted, if I go to Stat and in Summary Stats and go to Columns again, it brings up that pop-up window. And I'm going to click on the last column because that's the one that we're using. I'm going to click Next. And now what I want to do is actually copy this into the notes so that we can examine it. Okay, there's a couple things that I want you to notice. There's actually two more values beyond the unadjusted standard deviation. One is skewness and the other one is kurtosis. Not worried about that right now. You know that you can find this right here is the number of data values. That's your n. And it can be, right, it can be used for a population or a variance. I mean, not a variance, a sample variance. Okay, now, you're going to notice two things. You've got variance and standard deviation here, and you have unadjusted variance and unadjusted standard deviation here. This variance and standard deviation is for a sample. Okay? And it's going to use S is equal to the square root of sigma of x minus x bar quantity squared over n minus 1. All right, that's your standard deviation formula. So those two are for a sample. Where it says unadjusted variance and unadjusted standard deviation, That's for a population. And S is equal to the square root of sigma x minus mu quantity squared over big N. Okay? To be honest, the values are not going to be that different. It's going to be a small difference. But you've got to pay attention to the directions in my stat lab, because it's going to ask you to find the variance and standard deviation of populations and samples. Okay? Which means that if you use this for a sample, you're going to get it wrong. And if you use that for a population, you're going to get it wrong. Okay? Yes? That's supposed to be a sigma. I'm sorry. Thank you for pointing that out. Okay, that should have been a sigma. I apologize for that. I was thinking about everything else that I was trying to say at the end. I do that sometimes. I write down the wrong thing. Doesn't mean that I don't know what I'm doing. So, you know, you would think that, but I do. So my brain's going in a bunch of different ways, and I'm not one of these instructors that's going to get ticked off if you correct me, because I want you to do that. Okay? And if you notice that I make a mistake, say something, and I'm oh yeah, I made a mistake. Because we all do it. We're human. Humans make mistakes. Okay? Nobody is perfect. All right. Questions or comments so far? Okay, good. Now, let's talk about interpreting standard deviations. Okay? Let's interpret standard deviations. Oh, and actually before we do that, let me go ahead and let's go back to this right here. If I just go ahead and highlight variance and standard deviation, and I'm going to get rid of all the other stuff. I just want to look at, and I hit calculate. Let's look at the difference. Okay, notice that n is going to be exactly the same, whether it's a lowercase or an uppercase n. It's still only going to be 10 data values. The mean's not going to change either, right? Here's the variance for the sample, and here's the variance for the population. That's not a huge difference, but it is a difference. And this is lower because I'm dividing by a larger number. That makes sense, right? And look at the standard deviation for the population and the standard deviation for the sample. It's not a huge difference, but there is a difference. Okay? All right. Any questions? You guys following what I'm doing? And if I ever do something that you're not sure of, please say something. Okay? All right. Let's talk about how we interpret standard deviation, because what's the point of doing this if I don't know how to interpret it? Okay. First things, let's talk about interpreting standard deviation. It is a measure of the typical behavior of a data value. In other words, how much does it vary from the mean? Okay? Now, in this case, this is a frequency histogram of a data set that has a mean of 5 and a standard deviation of 0. Which means that all my data values occur where? At 5. Because if there's no standard deviation, that means there's no values that are different from the mean. Does that make sense? Okay. This one right here has a mean of 5 and a standard deviation of 1.2. Which means that I have an equal number of values to the left and to the right, and they're either going to be 1.2 away from the mean, or they're going to be 2.4 away from the mean, or they're going to be 3.6 away from the mean. Okay? Now, what about this one right here? This one has a mean of 5 and a standard deviation of 3. But what do you notice about that distribution? There's actually absolutely nothing in the middle, is there? Which means that all my data values occur way over here or way over here, but when I average them together, I get 5. And that is the point about how mean is affected by outliers. But what do we notice about the standard deviation? It's huge compared to the others. So that means I can determine some behavior characteristics of the data values. Ideally, what we want to do is we want to normalize or standardize our distributions, because we want them to look just like this. And you guys all know this because you have had to deal with it when you were in school, right? It's the bell curve. Every one of us has been rated according to the bell curve on some metric. You're in a math class. I calculate all your scores at the end of the semester, and I try to see if it's a bell curve. Why? Because our data, our research has shown that most standard distributions fall out with an equal amount of values to the left of the mean and an equal amount of values to the right of the mean. And the distribution tends to normalize like this. That means that if the average grade in this class happens to be a 75, that means an equal number of you will make less than a 75 as those who make greater than a 75. And that makes sense, right? Because that's the only way I can achieve an average of 75. If I have 20 people and 10 of them make less than 75 and 10 of them make greater than 75, those numbers will average out to a 75. That's what the distribution's saying, okay? I personally don't believe that all distributions have to be normalized, but that's just my personal belief as a statistician, and not all statisticians agree with me. There's a few of them out there who do. And I have come to that conclusion by taking classes, reviewing data out there, and reviewing the volume of material on distributions. But I do think that by normalizing a distribution, we can actually better interpret the data. Okay? So even if the distribution doesn't tend to be a standard distribution, we can standardize it. And you guys should all be familiar with that too, because how many of you in this class at one point took either the ACT or the SAT when you were getting ready to go to college? Most of you, or you should have. And if you haven't, that's because you're at a community college and we don't necessarily need ACT scores, because at a community college, we are here to serve the community. But if you guys decide to go on and get your 4-year degree after this, what do you have to take? Your ACT or your SAT, right? The American College Test or the Standard Aptitude Test. Now, both of those are what we call normalized or standardized tests. Because what they do is they take all the data collected over many, many years and they try to put it into a bell-shaped curve. Now, some people feel that that test is inherently biased, and it is. But you run that risk anytime you try to standardize something dealing with some sort of bias. And when I say bias, I'm not necessarily talking about racial bias or gender bias. Sometimes when I'm looking at a data distribution, it happens to be the size of cows after the drought last year. That could be a biased distribution. Why? Well, what if I didn't measure as many cows in the drought area as I measured outside the drought area. What would you say about my data? It's skewed. In order to make it a normal distribution, I need to measure the same amount of cows. And even if I measure the same amount of cows, there's going to be bias inherent in there because the drought area was huge. Texas, Oklahoma, a bunch of other states, cattle suffered, but they didn't suffer the same. Some had more problems than others. Hence the problem with statistics. Hence the reason we try to standardize these things. Now, I got 2 minutes. I got a minute and a half. You will notice right here in this bell-shaped distribution that 68% of your data will fall within 1 standard deviation of the mean. Within 2 standard deviations of the mean, you will have 95% of your data. And then within 3 standard deviations of the mean, you will have 99.7% of your data. That has been borne out over time by using careful studies. And this breaks down to something called the empirical rule. And basically what I'm trying to say is if your data happens to fall outside of 3 standard deviations from the mean, that's extremely unusual. And that study that I was talking about where we looked at income levels, the standard deviation for the African American sample in Huntsville fell somewhere close to 7 standard deviations from the mean, which means there was a huge problem with the data set. Whoever collected the data did a lousy job. Okay? And that's why we do things like this, because we can figure out if mistakes are made. And we can also figure out what's going on within these 3 standard deviations of the mean. Now, as I say, symmetric bell-shaped distribution, we're also going to call it a normal curve or a normal distribution. I pontificated for too long, so we're not going to get to Chebyshev's theorem, and we're not going to finish this section today. We will finish this section on Tuesday, and we will finish section 5 on Tuesday, so be expecting a test within the next week and a half. I will see you guys later. Have a good weekend.